In metric algebra, a very frequently used technique is the orthogonal projection. In this section, we'll consider basics for orthogonal projection, orthogonal sets, and orthogonal metric. See the definition. A set of vectors S, U1 to UP in Rn is an orthogonal set if each pair of distinct vectors from the set is orthogonal. That means ui dot uj is 0 for different ij. If the vectors in S are non-zero, then S must be linearly independent, and therefore the set forms a basis for the space spanned by the set. Orthogonal basis for a subspace W of Rn is a basis for W that is also an orthogonal set. This theorem shows one of the reasons why orthogonality is a useful property in vector spaces and metric algebra. U1 to UP is an orthogonal basis for a subspace W of Rn for each y in W. The weights in the linear combination are obtained by this equation. Because it is a basis for each element, each vector in W, we can write in this way. Always, by using the basis vectors, we can express y in this way. Now the coefficients can be obtained through this quotient. So you can decide the weights quite easily here. And from this equation, we may take dot product with uj. Then now here we have that one. Because these are orthogonal, then only uj dot uj remained, and for other vectors, the dot product will be 0. So we recheck this one, and this is the same as now uj norm squared. Anyway, here cj can be decided by dividing this quantity, and we recheck this one. Okay. So quite easily we can decide weights. Consider a set of vectors u1, u2, u3 here is as orthogonal. Express the vector y as a linear combination of the vectors in S. Okay, first we have to figure out the set is orthogonal. Okay, dot A and u1 dot u2. Two vectors we make a dot product 0 minus 2 plus 2. Okay, it is 0. How about u1 dot u3? Here u1 and u3 minus 5 plus 4 plus 1. Okay. Yes, again 0. How about u2 dot u3? Okay, from here to there, 0 minus 2 plus 2. So again, this is 0. So the set of these three vectors is orthogonal. Now, for part B, we'll try to use that one. Y is given here, and if we try to express this y here in C1 U1 plus C2 U2 plus C3 U3, then Cj can be decided by this equation. So let's do that. Here C1 is now y dot u1 divided by u1 dot u1. Okay. Y is okay. We'll try to write down y vertically so it's easy to handle. So that y is 11, 0, minus 5. Okay, that's y. And y that you want, 11. That is 0 and minus 5. So that is 6 divided by u1 dot u1, 1 for 1. So it's 6. So we have 1. How about C2? That is y dot u2 over u2 dot u2. Okay. Y u2, 0, 0, minus 10. Divided by u2 dot u2, 1 plus 4, 5. So it is a minus 2. Finally, we have to get C3. That is y dot u3 over u3 dot u3. Okay. Y dot u3 minus 55. Okay, let's try to write. Minus 55, 0, and minus 5. And divide by, okay, 25, 4, 1. Addition is 30. Top is minus 60. So that is minus 2. So we have C1 is 1, C2 is minus 2. Again, C3 is minus 2. So eventually we'll get that answer, right? Okay, quite simple. Now we'll begin orthogonal projection. Given a non-zero vector u, okay, start with a non-zero vector u in Rn. Consider the problem of decomposing a vector y into sum of two vectors, one a multiple of u and the other orthogonal to u. That means y is y hat plus c. Now y hat is parallel to u. That is same as 1 multiple of u. That is y hat. So that y hat is parallel to u and z is orthogonal to u. So in this way, we try to decompose the vector y. Okay, y hat is parallel to u. We may start with that one. Y hat is alpha u. Then here z dot u, because it's orthogonal, dot product must be 0, but z is the same as, okay, we move this one to the left hand side, so that z is the same as y minus y hat, we say that is alpha u, so it is a y minus alpha u. So that is exactly this one, dot u. Then that is same as y dot u minus alpha u dot u. Okay. Known value, known value. So alpha can be found here after moving this one divided by u dot u. So we reach it there. Right? So here, pictorially, this is u, a non-zero vector. Y doesn't have to be non-zero in this theory, but y is non-zero. Okay, this is non-zero. And y is now, it is decomposed into two portions. There is y hat here, and then z, so that this is orthogonal. In this way, and move y hat in the direction of u, and then orthogonal direction z to reach at y. So there is y hat plus z decomposition. Pictorially, we can consider this one. Now we define our derivation here in this way. Given a non-zero vector u in Rn for Ys in Rn, let Ys, y hat plus c, and y hat is parallel to u, and now z is orthogonal to u. Then we may start with y hat is alpha u because it's parallel to u, and alpha can be found, already we found here, y dot u over u dot u, right? So we have here. And once y hat is determined, then z can be decided by subtracting y hat from y, right? So we can decide that, right? That is definition. The vector y hat is called the orthogonal projection of y onto u, and z is called the component of y orthogonal to u. Now, rather than a vector u, and we consider space, subspace L spanned by u. Of course, that is a line. Here, so L, so it's a line. Then we can write in this way the projection onto u. Rather than projection onto u, we consider projection of y onto L, so that y hat can be written in this way, projection of y onto L. This one is more convenient to listen as. Okay, in this case, the angle here is acute angle, but maybe you may have to deal with obtuse angle. Y is in that direction. Then projection will be opposite of u, so that that is projected one. There's y hat, and there will be c. So looks like far away, and maybe a bit odd. U is that one, but there is no u here. So that rather than u itself, we consider the whole line. So whole line is L, the subspace, and using L, we try to consider the projection. Then more meaningful and also geometrically more sound, right? Okay. See the example. Y and u are given. Find the orthogonal projection of y onto u. We'll say from time to time onto u. However, rather than u, you have to consider here onto L. It is span of u. Okay. Okay. So you have to understand with this. Okay. Let's begin. A. And y is projected onto u, which means y is now y hat plus c. Of course, here y hat will be here alpha u, and alpha is y dot u over u dot u. Y dot u. Y dot u, that is 28 plus 12 divided by, and 16 plus 4, u dot u, 16 plus 4, bottom is 20, top is 40, so it is 2. Right? So y hat is the same as 2 of u, which is now, okay, 8 and 4. So that is exactly the projection itself. So we did that is the projection. Write y as the sum of two orthogonal vectors, one in the space L, span of U, and one orthogonal to U. Now we found already this one, and then Z must be found. Okay, that is part B, is y minus y hat. Okay, y is 7 and 6, 7 and 6, and Z, okay, y hat, okay, y hat is 8 and 4. So that is here minus 1 and 2. Right? So if we try to write it once more, then we can write in this way. Y is now y hat plus Z. Now y hat is 8 and 4. And Z is now minus 1 and 2. Right? So that you can easily see that addition is 6, and now addition is 7, right? And also, you can see dot product of these two vectors will be 0, minus 8, plus 8. So it is 0, right? So everything is satisfied. Now, find the distance from Y to L, okay? Now, U is, okay, part C. Here, you see that one. The space L is this one, and Y is this one. And it is projected to U here, and there's Y hat, and there's Z. Okay, this one is now Z. Once we try to find distance from here to there, then there is exactly now y minus y hat, which is Z. So distance is norm of Z. Right? So that is norm of Z. Okay. And that is, okay, Z is already known here. Minus 1 and 2. So the square root of 1 plus 4. So it's the square root of 5. The final answer for C is square root of 5. Okay. Now, orthonormal sets. A set U1 to UP is an orthonormal set if it is orthogonal and having unique vectors. All vectors has length 1 and they are orthogonal. Then it is called orthonormal set. If W is a subspace spanned by such a set, then the set is on orthonormal basis for W, and orthonormal basis, the set is the basis requires linear independence, but the orthonormal, then automatically it's linearly independent, so that the set spanned by this orthonormal set, and then the orthonormal set must be orthonormal basis for W, right? Orthonormal, then automatically linearly independent, right? In example 9.18, we know V1, V2, V3 form a orthogonal basis for R3. Find the corresponding orthonormal basis. Okay, already we know V1, V2, V3 are orthogonal. Now, orthonormal basis requires normalize the vector. So we can get easily by normalizing these vectors. So U1 from V1, we normalize it. So divided by V1 norm. Okay. So here length is 1, 4, 1. So square root of 6, 1 over square root of 6, and V1. V1 is 1 minus 2 and 1. How about U2 is from V2 normalized, V2 norm. Okay, from V2 norm is now square root over 5, 1 over square root over 5, and V2, which is 0 and 1 and 2. How about the last one? U3 is V3 normalized. V3 norm. Okay, V3 norm. Here 25, 4, 1. Okay, 30. So it is square root of 30. And V3, which is minus 5, minus 2, and 1. Right? So we found the corresponding orthonormal bases. They are orthogonal, either normalized or not. They are orthogonal. But after normalization, the length of each vector will be 1. So these 3 vectors will form on orthonormal basis. On m by n, matrix U has orthonormal columns. Okay, each column is now normal, length 1, and they are orthogonal each other. So orthonormal columns, if and only if U transpose U is identity. Let's try to prove it. For simplicity, we start with the case U has only 3 columns. U is U1, U2, U3, and each one is in Rm. Then, now U transpose U, that is explicitly written in this way. Then we do matrix, the row column multiplication. U1 transpose U1, that is this one. U1, this is a row vector right now. This is column vector. U1, U2, that is this one. U1, U3, that's one. You continue and you make this 3 by 3 matrix. Now, U has orthogonal columns. Assume this one. Then orthonormal means this diagonal must be 1, but up diagonal entries must be 0. So we reach this one. And also, once it is true, then that means that this must be 0, and only along diagonal the value must be 1. Also, the below must be 0. That is exactly saying that the columns of U are orthogonal and length 1. So U has orthonormal columns. So they are equivalent when U has 3 columns. However, this proof can be expanded for general number of columns quite easily. We start with 3 columns for simplicity, but for general number of columns, you can do you can finish the proof. So generally, that is true. Okay. Now U is on m by n matrix with orthonormal columns, which means that if and only if, we already know from the previous theorem that is U transpose U is identity, right? Now we choose xy from Rn, then Ux norm is same as x norm, So it is a length preservation after multiplication of u. ux dot uy is same as x dot y. That is dot product preservation. And ux dot uy equals 0 if and only if x dot y equals 0. The orthogonality preserved. Let's prove the theorem. Okay, part A. Now, we think here ux, now norm squared. Then they're the same as ux transpose ux. Now, from this part, we have x transpose u transpose. Now, u and x. This portion is identity, right? So here that is same as x transpose x, which is same as x dot x or x norm squared. So after eliminating the power 2, we reach that, right? Part B. And here ux dot uy, we start with here ux dot uy. They're same as, in fact, ux transpose and uy. Right? So from here again, using this one, x transpose u transpose uy. Okay, this portion is the same as that one. Now, u transpose u is again identity, so we reach at x transpose y, which is same as x dot y. So we proved this, the second one. The part C can be proved quite similarly. You can finish it yourself. Theorems 9.23 and 9.24 are particularly useful when applied to square matrices. Okay, let's go back to the theorems. These two, okay, and its general size matrix U, Mn, matrix U has orthogonal columns if and only if U transpose U is identity. And once U has orthogonal columns, then the matrix preserves length, dot product, and orthogonality. Now we consider the case when U is a square matrix. So you see n by n matrix. And in this case, it's quite useful and frequently used. So we give a name. The name is orthogonal matrix. An orthogonal matrix is a square matrix U such that U transpose is U inverse. That means it is invertible square matrix and the inverse is U transpose. We may rewrite in this way. U is a square matrix and U transpose U is identity. U transpose is, now after the product it becomes identity, so that U transpose is U inverse. Now once this one is satisfied, then U has, if and only if, U has orthonormal columns. But the matrix name is orthogonal matrix. Traditionally in mathematics, mathematicians use this name, but you should not be confused. Just this is a name, but practically orthogonal matrix, then practically is a square matrix and invertible, and also each columns are orthonormal vectors, and also it is a satisfying U transpose U is identity. Don't be confused with the name. it is orthonormal columns. Okay. Let's generate a random orthogonal matrix and test it. Here we choose n is 4. So we try to make 4 by 4 orthogonal matrix and generate a random 4 by 4 matrix and QR factorization. And you will learn QR factorization in section 9.4. Then here Q is always orthogonal matrix. We are using U notation. So after getting it, now now change into U. And then now here we try to print out the matrix U, and U transpose U must be identity. And here we get a random vector and print out and check the norm of X and norm of UX. It's a norm preserving, so the output must be the same, right? Okay, here we have output. U, that is randomly generated orthogonal matrix, and U transpose U, see here, and diagonal is 1, and up diagonal entries are 0. So it is basically identity. And this vector is generated, and its norm and UX norm, they are the same, right? Okay, that's the end of the section. Thank you.